Welcome back. In this video, we are going to finish the exercises of chapter 4. Exercise 12 is a generalization of a result known in Hilbert spaces. So recall that if you have a Hilbert space and you have a non-empty closed convex subset of K, and you define the distance between a point X in E and K as in the usual way, as the infimum of the distances between X and points in K. Then there exists a unique Y where the infimum is achieved. Okay. In general, the infimum is not a minimum, but in Hilbert's case, and here in the more general context of a uniformly convex Banach space, the infimum is achieved at exactly one point Y. Okay. And in this case, the point Y, in the case of a Hilbert space, we call Y, this unique point, the projection of X onto K. Okay. So I think that this was a preliminary step to prove Reed's representation theorem in second year. Okay, so here we want to do the same thing, but in the more general context of a uniformly Banach space. Now, if D is 0, there's really nothing to prove, because if D is 0, then X belongs to K because K is closed, as you know. So the xk is 0 if and only if X belongs to the closure of K, but since K is closed, so therefore we assume that D is strictly positive, and therefore X is not in K. So try to draw a figure to accompany this exercise. Take a convex set and point X outside and try to do some kind of projection onto K. So for this, we follow a plan, and the first step we have to show that there exists a sequence Y and K whose distance to X converges to the infimum. And then we introduce a sequence Zn in the unit sphere, which is just X minus Yn over its norm, and 1 over X minus the Yn, the norm of X minus Yn, we call it Tn. So it's a real number, positive real number. So we have to show that Zn plus Zm in the norm is bigger or equal than Tn plus Tm times the infimum. And we have to deduce from this that Zn is a Cauchy sequence, and then we have to use, of course, completeness to find an element Y solving this problem. Okay. So the first point is very easy, actually. It's just a consequence of the definition of the infimum. So if D is the biggest lower bound, it means that D plus any positive number is not a lower bound. So we can find an element in the set which is less than the infimum plus this positive number. So therefore, this sequence Yn satisfies that the norm of X minus Yn converges to D by the sandwich theorem. Okay, this is easy. Now, so as we said, Zn is in the unit sphere, and Tn, according to what we said, converges to 1 over D. So we go back to the definition of Zn. So we write Zn plus Zm as Tn x minus Yn plus Tm x minus Ym, and then we factor by Tn plus Tm, which is strictly positive, actually. And now we rewrite this. So we have Tnx over Tn plus Tm plus Tmx over Tn plus Tm. So this makes X, actually. So, and then we write Tnyn over Tn plus Tm plus Tm Ym over Tn plus Tm. So why did we do this? Because Yn and Ym are in K, and the term in parentheses actually is what we call a convex combination of Yn and Ym, because the coefficients are positive and they sum to 1. So therefore, the term in parentheses, since K is convex, belongs to K. Therefore, when we take the norm, we get Tn plus Tm is positive, times the norm of X minus this guy. And this is, of course, bigger than the infimum, because the infimum is the lower bound. And that's it. So this is just Tn plus Tm times D. Okay. Now, to prove that Zn is a Cauchy sequence, the easiest thing to do is to reason by contradiction. So suppose that Zn is not a Cauchy sequence. So then we go back to the definition in terms of quantifiers. So there exists epsilon positive such that, etc. And then you will find that there are infinitely many couples N and M, such that Zn minus Zm and a norm is bigger than epsilon. Or equivalently, for every K there exists N, there exists M bigger than K, satisfying this. So this is just the negation of the Cauchy condition. And now if you take delta to be the modulus of uniform convexity, so to go back to the definition, this means that the norm of the middle point of Zn and Zm is less than 1 minus delta. And according to the previous question, this is bigger or equal than Tn plus Tmd over 2, because you divide by 2. Now, this is true for every n and m, but this inequality need not be true for every n and m. It's true only for n and m satisfying this, but there are infinitely many couples which satisfy this. But it doesn't really matter, because if this is true for infinitely many n and m, we can take n and m as large as we wish. And so when we let n and m tend to infinity, what happens? Tn converges to 1 over d, and Tm converges to 1 over d. Therefore, Tn plus Tm, as n and m get bigger and bigger, converge to 2 over d. So we get 2 over d over 2 times d, which is 1. Therefore, this converges to 1. And so, therefore, at the limit, we get 1 is less than or equal than 1 minus delta. Okay. Or if you like, if you don't know that Zn minus Zm is convergent, you just can take the lim sup, actually, it doesn't matter. So you can just take lim sup of this less or equal than lim sup of this, and this is less or equal than 1 minus delta. So, okay, well, actually this term doesn't bother me. So just write this, Tn plus Tm over 2 times d is less or equal than 1 minus delta. Okay, so therefore the limit of this guy is less or equal than this guy. So get 1 less or equal than 1 minus delta. And this is, of course, a contradiction. Therefore, Zn is a Cauchy sequence. And now, since the space is complete, Zn converges to some limit z. So since Zn, the norm of Zn is 1, then the norm of the limit is also 1. And by definition, we can write Yn equal x minus 1 over Tn Zn. And since Zn converges to z and 1 over Tn converges to d, then, and this is a constant, so Yn converges to x minus dz, and I call this y. Okay. And this will be my solution. So therefore, if Yn converges to y, then by continuity of the norms, x minus Yn norm converges to the norm of x minus y, but x minus Yn and norm converge to d by construction. Therefore, by uniqueness of limits, d equal to norm of x minus y. And of course, y belongs to k because k is closed. Because Yn is a sequence in k, so the limit must be in k. So this proves the existence part. Now, for uniqueness, we have to use the uniform convexity condition again. So suppose that there are two solutions to this problem, y and y prime. Then we take d, so we have d equal to norm of x minus y, and it's equal to also as well as norm of x minus y. So norm of x minus y prime equal norm of x minus y equal d. And if y prime is different from y, then the distance between them is positive, and we take this number to be epsilon. Now, if you recall a remark in the lectures that if the space is uniformly convex, and this means that the sphere is uniformly round, then any sphere is also uniformly round. So this, I hope that you proved that actually, because I gave it as an exercise. So now, if we write the condition of uniform roundness of the sphere of center 0 and radius d, this means that for any u and v in the unit sphere, if their distance is bigger or equal, doesn't matter to epsilon, then the norm of the midpoint is less than d minus a number delta, which can be called the modulus of uniform convexity. Now, norm of y minus y prime is also equal to norm of x minus y prime, because these two cancel. And according to this definition, and of course x minus y or x minus y prime are both on the unit in the sphere of radius d. Therefore, according to this condition, the norm of the middle point is less than d minus delta. Okay, so so we have x plus x over 2, which is just x. So we can write it as norm of x minus the midpoint of y and y prime is less than d minus delta. And convexity of k, since y and y prime are both in k, then their middle point is in k because k is convex. Therefore, the distance between x and the middle point is bigger or equal than the infimum. So we get d is less than d minus delta, and this is a contradiction. So therefore, y is necessarily equal to y prime, and this proves uniqueness. So this concludes exercise 12. Exercise 13. Also, it's an extension actually of a result in Hilbert spaces. So, but I don't know if you took it. We have a uniformly convex Banach space E, and we have a sequence Xn that converges weakly to X, but we have an extra assumption. In general, we cannot conclude that Xn converges strongly to X, okay? Because we gave an example, and we shall give more examples later. But here we have two extra assumptions, actually. We have the assumption that norm of Xn converges to the norm of X, and we have the fact that E is uniformly convex. So we have to use these two assumptions to conclude that Xn converges to X. Now, if X is 0, then norm of Xn converges to 0, and this precisely means that Xn tends to 0. So there's nothing to prove. So therefore, we deal with the case where X is not 0, and therefore we can divide by the norm of X. And we write Xn minus X in the following way. We divide and multiply by norm of Xn, which actually makes sense because if X is different from 0, norm of Xn converges to something positive. It means that Xn cannot vanish from a certain rank. So it's different from 0 from a certain rank. Therefore, norm of Xn is different from 0, so we can divide as well by norm of Xn. So, but then we add and subtract norm of Xn over norm of X times X. Why are we doing so? Because now we look at the first two terms, and so we can use the triangle inequality. The norm of these two guys, so the norm of Xn minus X is less than the norm of these two guys plus the norm of these two guys. Now, if you look at these two and take the norm, then we have norm of Xn in common, and then we just have the norm of Xn over its norm minus X over its norm. This for this first two. And now, if you look at these two terms and take the norm, then you will have actually norm of X in common. But I'm having also norm of X in the denominator, so they cancel, and I just get norm of Xn minus norm of X in absolute value. Okay, now we want to show that this quantity tends to 0 as n tends to infinity. If you look at the second term, there's no problem because this term here tends to 0 by assumption. Okay, so we just have to prove that the first term tends to 0, and then we will be done. So we introduce a new sequence, yn, which is xn over its norm. So it's a sequence on the unit sphere, and we let y to be x over its norm. Therefore, we have now a sequence in the unit sphere yn. And you may check actually that yn, since xn converges weakly to x, try to prove that yn plus y over 2 converges weakly to y by going back to the definition. Actually, it's a good exercise and could be an examination question. Actually, I asked this before. Okay, so therefore yn plus y over 2 converges weakly to y, and according to chapter to the consequence of the uniform boundness principle, the norm of the limit is less than the lim inf of the sequence. Okay, and once again we took lim inf because we don't know yet that yn plus y over 2 converges. Actually, it will be conversion, but we don't know that yet. So we took the lim inf. Okay, so 1 is less or equal than the lim inf of yn plus y over 2, and on the other hand, the norm of this middle point by the triangle inequality is less than 1/2 times norm of yn plus norm of y, which is this is 1, so it's less or equal than 1. And therefore, now since we don't know that yn plus y over 2 converges, we just take the lim sup. The lim sup of this is less or equal than the lim sup of this, which is 1. But then actually we have that the lim sup is less or equal than the lim inf, less than 1. So actually both lim sup and lim inf are equal. And therefore, in this case, we know that the sequence is convergent and the limit is the common value of these two. So we know now that yn plus y over 2 norm converges to 1. And as you know from uniform convexity, this implies that yn minus y in norm tends to 0. So if you go back to the equation, so this is just yn minus y, it tends to 0. And since xn is conversion, then of course, so this tends to norm of x, this tends to 0. Therefore, the first term tends to 0 as well. Even if norm of xn is not convergent, it's just enough to be bounded. Okay? Because bounded times something that goes to 0 goes to 0. Therefore, yeah, so this concludes the proof. Okay, now last exercise. I mentioned it in the lectures actually. We have an infinite dimension norm space, and we consider the function from E to R given simply by the norm of x. Call it phi. The first question, we have to find the inverse image under phi of the open interval 0, 1. Then we have to deduce that phi is not weakly continuous. Okay, but it's strongly continuous, as you know. This is a counterexample. Now, the inverse image of under phi of 0, 1 is just the set of x whose image under phi is between 0 and 1, by definition. And this is just what? This is just the open unit ball without the center. Okay? So, in particular, it's a bounded set. But we know that if the space is infinite dimensional, the weakly open sets are unbounded. So, this set cannot be weakly open. Therefore, we found an open subset of R whose inverse image under phi is not open in the weak topology, therefore phi cannot be continuous. You can ask such question in the exam. Okay, so. However, there are some remarks that I have to end with. We can prove more by the same reasoning. Phi is nowhere weakly continuous, not just because saying that phi is not weakly continuous means that there is a point where it is not weakly continuous, but actually you can prove that phi is nowhere weakly continuous. Why? Same reasoning. Pick any point x0 in E and consider the neighborhood of norm of x0 or phi of x0. So phi of x0 minus 1, phi of x0 plus 1. This is just an open subset of R. So this is a usual open neighborhood of the norm of x0. Now, if U is a neighborhood of x0 in the weak topology, then as we said, U is unbounded. However, if phi was continuous at x0, then we would have a neighborhood U of x0 in the weak topology whose image under phi is contained in V by definition of continuity. Okay. If this is true, actually, then the norm of x, which is phi of x, would be in V. So it would be less than norm of x0 plus 1. Okay. So this means that x is in a ball. So this means that U is bounded. Therefore, there's no such weak neighborhood. Therefore, phi is not continuous with respect to the weak topology at x0. Okay. So this is an example of a strongly continuous map from E to R, which is nowhere weakly continuous. Now, however, if either E star is separable or E is reflexive, then phi is not even sequentially continuous. Weakly sequentially, not weakly sequentially continuous. Why? Because if you recall exercise 9, we have a sequence xn in the unit sphere that converges weakly to 0. But phi of the sequence is just norm of the sequence, which is 1. So it does not converge to 0. Okay, so please just add, is not even weakly sequentially continuous. Third remark, if you consider the space small L1 of sequences, of summable sequences, it has a surprising property called the Schur property. In this particular, not in this particular space, a sequence is convergent, strongly convergent, if and only if it is weakly convergent. Okay, so the two notions of convergence coincide, although the two topologies, the weak, strong, do not coincide. But these two topologies have the same convergent sequences, and this is something really specific to L1. It's not true in any normal space. Okay. You can find this proof in problem 8 in the book of Prezis, if you like. So therefore, if we take E to be L1 and take phi to be the norm 1, then this phi is weakly sequentially continuous everywhere, but nowhere weakly continuous. Okay. Why is it weakly sequentially continuous? Because if xn converges weakly to L1 to x, then it converges strongly, and therefore the norm of xn converges to the norm of x. Okay, so I have to distinguish here between the two notions of continuity and sequential continuity. In the case of a metric space, these two notions are the same, as you know, but we pointed out that this is not true in an arbitrary topological space. So we have to distinguish between continuity and sequential continuity, and also between compactness and sequential compactness. And last remark, we say that the function phi is weakly lower semi-continuous. This is an important notion that we'll study in the calculus of variation. What does this mean? It means that the inverse image under phi of a closed interval of the form -infinity a is weakly closed. Now, try to prove that, actually, because I may ask you this question in the exam. It's so simple. Okay, so this concludes the exercises of chapter 4. Thank you for your attention, and see you next time.